Good morning, good afternoon, or good evening to all of you based on your current time. This talk is about identifying privacy weaknesses for multi-party transaction integration platforms. I am Kulani Mahadeva from National University of Singapore. Let's first see what are transaction IoT platforms. These are a type of IoT application platforms which enable integration of multiple third-party online services, including IoT and non-IoT. With this integration, it enables diverse automation possibilities through simple if-then conditional rules. Currently, the most popular transaction platform is IFTTT. It has about 19 million users worldwide with more than 700 services integrated. The other platforms include Zapier and Microsoft Flow. To use this platform, the user first need to create an account from each of these services. Next, need to authorize the connection of these services with the transaction service. After that, the user can specify the automation rule through an applet. For example, if new photo upload at Facebook, then turn on new likes. This study, we focused on this cloud integration. Due to the cross-party cloud integration, there could be privacy issues in transaction platforms. An example is cross-party policy infringement, which means the policies defined by at one service could be violated by another. For example, when this applet executes, the private photo at Facebook could be transmitted to the transaction service. However, the privacy could be downgraded such that it owns a publicly accessible URL of the photo. We identify at least two causes for privacy issues. One is misunderstanding on the shared responsibility by the integrated parties. This integration involves interfaces provided by each of the parties. However, there is lack of coordination between them to provide necessary support for the user to control their private data. Second, lack of comprehensive testing. This is challenging due to the exponential growth of integration possibilities. So we answered the question, how to identify privacy weaknesses from transaction integration platforms that we call as types. The main challenge is the closed source nature of the types. We proposed an approach called TYPHO to identify privacy weaknesses of types. It automatically generates applets to probe different types. When applets are executed, it automatically extract behavior data from the client applications to infer the type's behavior. Next, we characterize and check 5 types of privacy violations using a set of rules applied on the extracted behavior data. To explain the approach, I'm using an example of this applet. The rule is if a photo upload at Facebook trigger happens, then perform the light turn on action. The user specifies this rule through an applet generation request. The applet is generated in the cloud. So we need to perform an external event to execute this, which is the trigger event. Then the applet executes and performs the action. Additionally, some information related to the applet's execution is received by the transaction client. We first characterize privacy violations in a type. We refer to GDPR, General Data Protection Regulation, since there are a lack of existing documentation or guideline for data privacy of types. In Article 5 of GDPR, which is on personal data processing, it lists 6 principles. These include the data should be processed lawfully, fairly, and in a transparent manner. When the data collected, it should be limited to the purpose as well as it should be limited to the necessary amount of data. Data should be accurate, so it should be keep up to date as well as when it is no longer needed, it should be removed. Also, the data should be processed in a manner that ensures the security of the personal data. Based on these principles, we identify 5 types of privacy violations in a type. First, access control policy breach. Second, lack of access revocation. Third, unintended data loss. Fourth, lack of fine-grained access control. Fifth, lack of least privilege enforcement. Our approach takes 3 inputs. Service corpus includes information about the online services, credentials of the user account, and transaction client. We first generate a set of applets. To generate before generating the applets, we need to connect the services with the transaction service. This involves authentication and authorization using the credentials. We automate this for the IFTTT platform. It involves clicking on the connect button, providing credentials, clicking on sign in, and allowing connecting the service. We connect several services for testing purpose. Next, we generate the applets. This involves generation-based test cases. So we first manually extract the common protocol steps in the applet generation protocols. This includes a selection of a pair of trigger and action events, then requesting for the event configuration fields. For some values, we can obtain the list of values we call options. Next, we need to provide values for all the fields. So in this case, we simply select one from the received options. We send these values to the trigger action service, generating the applet in the cloud. We repeat these protocol steps for different event pairs to generate more applets. These applets are next input to the applet executor and behavior monitor. To execute the applet, we need to perform an external event, such as uploading the photo. To simulate this trigger, we need to own this HTTP post request. Next, we mutate values related to privacy as well as data types to generate more or simulate more events for testing purpose. During this time, we perform behavior monitoring. The sources for behavior monitoring are the client applications. The trigger client and the action client are web applications. So we take two instances of these web clients with respect to the applet's execution. Next, we use differential analysis to obtain the altered data. This data include text and URLs. The execution history is received from the trigger action service. This is a well-formatted JSON structure, so we refer to keys to extract data. Next, these behavior data along with the applet configuration data we input to the privacy checker. Also, it uses a keyword corpus which includes privacy-specific terms. So this is how we define the privacy violation in terms of type. First, user given access permission for the trigger data at its creation should contain in a type. Otherwise, lack of access, access control policy breach exists. Second, once the user deleted trigger data from the trigger service, deletion should continue in the type. Otherwise, lack of access revocation exists. Third, only the user intended data should be acquired by the type. Otherwise, unintended data flows exist. Fourth, if trigger or the action service provide access control to its data, then type should propagate that to its users. Otherwise, lack of fine-grained access control exists. Fifth, only the minimum amount of trigger data should be acquired by the type to complete the automation task. Otherwise, lack of least privilege enforcement exists. To check access control policy breach, we need to know this user given access permission. We could know that from the trigger client. Next, we need to know what is the privacy of the trigger data in the services. We use behavior data for this since it reflects the services behavior. To infer the privacy of text, we check for keywords. To infer the privacy of URLs, we weave them as a public user. In this case, we can see that the resource URL owned by the trigger action service is public, although it's private initially. So this violation exists. To check lack of access revocation, we delete the photo and then we again check for the accessibility of the URLs. In this case also, although the photo was deleted, we can see the resource URL owned by the trigger action service is still accessible and public. To check unintended data flows, we answer the questions. Is the simulated trigger data user intended? And does type acquire unintended data? The rule is that if the simulated trigger not equal to the defined trigger but applet executed, implying that the type has acquired the data, then this violation exists. To check the first condition, we refer to the applet rule. We simulated upload video, which is not equal to the defined trigger. Next, to check the second condition, we refer to behavior data. So in this case, the applet was not executed, so it's false and this violation does not exist. To check lack of fine-grained access control, we answer the question, does service provide access control to its users? Does type propagate that control to its users? The rule is, if service provides privacy configs, but type does not propagate that to its users through event configurations, this violation exists. To check first condition, we refer to initial knowledge. To check the second condition, we refer to applet configuration data. There are no privacy-related terms there, so this is false, and this violation exists. To check lack of least privilege enforcement, we answer the questions. What is the minimum amount of data required? Which data type has acquired during the execution? In the context of type, we apply this to a resource URL of the trigger data. So if the resource URL of the trigger data does not require for the automation task, but type has acquired the resource URL, then this violation exists. To check the first condition, we refer to the applet configuration data. There are no mentioning about resource URL, so it's false. To check the second condition, we refer to behavior data, and we can see that the resource URL was acquired. So this violation exists. To evaluate the accuracy of our approach, we check for existing benchmark. However, we couldn't find existing benchmark related to or have used in similar study. So we manually crafted ground truth. It's a data set about of 127 applets. We check for the recall to check with our approach how good at it accurately identifying parameters to the privacy checking rules. So these are the results we got. I highlighted the highest precision and recall. The reason for these highest values is that this data does not have many noise since they are extracted from the JSON structured data. The less precision recall in other cases are due to the noise in the data extracted from the web applications. However, with these results, we can conclude that our approach is good enough in identifying privacy weaknesses. Next, we evaluate effectiveness of our approach. We generated 407 applets from 52 services. This includes 13 sensitive trigger events. From them, only 283 were successfully executed, and these are the results for the 5 types of privacy violations. From this, we can see that access control policy breach and lack of fine-grained access control are the most common. Lack of access revocation and lack of least privilege enforcement are less common, and the least is the unintended data flows. We also evaluated automation failures of our approach during the authentication and authorization. And when there are additional verification, we couldn't automate them. During the applet generation, some values were incorrect given to the event configurations. During the applet execution and behavior monitor, we faced some login or server-side errors, and also from the successful login cases, we didn't have IoT devices, and some triggers involve money, so we couldn't test them. In summary and conclusion, we identify privacy weaknesses from closed source multi-party types by proposing a black box testing technique. We characterized and checked for 5 types of privacy violations of multi-party types. We applied our approach to the most popular trigger action platform, which is IFTTT, and demonstrated that there exist privacy weaknesses in the IFTTT by detecting 490 violations by the applets. So this is about our work. Thank you very much for listening.